Okay, so yeah, so covered that pretty much. Looked over the useless function. Not sure if you looked at the higher order functions there. Yeah, I think we went over that, which is basically just how the functions can be ordered and how they can work to achieve particular stuff. The what if. Yeah, pretty much I think we looked at this as well, which should just basically run as intended, which we'll take a look at as well, which is basically an if statement, and looking at how that particularly works. Right, so without functions, exceptions. Right, so I think what let's look at the recursive is it's a lot to take in, to be fair. There's definitely a lot of code here, and some people are just working on specific data types or specific data types, so lists mainly, and just performing various tasks upon those lists. This tail latent zip, it basically joins together two lists. So for example, if I come to this particular section here where I have an Erlang shell running, and I compile the recursive L function there, which basically compiles okay, and then we define two lists. List 1 equals 1, 2, 3, 4, 5, 6, 7, 8 for good luck, and we have list 2, which defines A, B, C, D, E, F, G, H. Cool. Alright, so we've defined those. So let's see what functions we're going to take a look at there. So I think a good one to start with would be function here. So let's see what, I think we'll start with the basic let's see. Alright, let's just take a look at the first one here, which is basically I'm an error code when performing the function. I'm trying to run the function. Okay, so sorry, my bad. This one doesn't actually take a list. It takes whatever value we give it. So if we give it the value 5, we get back 20. So if we give value 2, get back 2. So basically just factors a number. If we give it the value 3, we get back 3. It's pretty straightforward, and then we have length here. So as you can see here, it just times the number, and if it's 0, it just brings back 1, and when n is greater than 0, it times that number and then sort of accumulates onwards using using that particular number. And then here we have length, which basically calculates the length of a list that we supply to it. So see here, if we just do length and supply list 1 gives us 8 because that's a number in there, and if we do list 2, it can be a list of any type. I think it's pretty straightforward. Like as you can see here, you supply it with a value, and what it does is it removes using the head function. Tail is whatever is remaining, and it basically runs the length function on that, and if there's anything left there, it basically adds 1 and so on and so on and so on until there's an empty list, and then you sort of get the value for that. In the long run, this one here removes duplicates. Using the head there, so it takes this value here and then pretty much checks it against the, so if we do list 1 and then plus 4, this should be pretty much fine. Oh no, sorry, my bad. I have to just create a dupe list. And if we pause dupe list, okay, I need to review this duplicate function again. So hazzy the duplicate function is a bit iffy because the parameters that I'm passing it aren't really being recognized as I generally intended. Unless if it's if it does something. Unless if it works a little bit different than how I'm actually anticipating. So maybe it actually duplicates. So if I say term hello and I put the value 3 here. Okay, alright, cool. So that's what the function does. My bad. Wasn't reading it right there. So you put the number and then basically, as you can see here, you put the number and then when it's less than 0, it basically duplicates that term by appending it to the beginning of the list until the number basically reaches 0 pretty much. And then tail duplication pretty much does the same thing but in a reverse order way. So tail duplicate here, as you can see, it's yeah, it's pretty straightforward. It does the same thing, but in a reverse fashion. But here's what term and list, which is a bit different to what I'm intending, or what I'm at least expecting. So it takes number, term, and list. Okay, so it takes list only here after you've actually supplied the number and the term. After you've only supplied the number and the term, and then after that, because it needs to pass in the list so that it can actually begin to append that term to that particular list, of which list here, from my understanding, would be an empty list. Yeah, but I believe that it needs that in order to actually append that term. Though I would have actually, yeah, no, I think it should be fine. So we can see here how the recursive duplicate here works, which is a one that's using the head instead of the tail, whereas the one that uses the tail duplicate, still it takes the value, but it still returns the same thing, as you can imagine. But as you can see here, that the way it does it is a bit iffy, in my own personal opinion, because it nests the list. So that's what I didn't really understand here about why it's doing this, why list is actually required here. I think we could actually remove list, and that'll probably be better for it. So for example, you could do something like instead of term list here, you could have it's risky. You could maybe have head. So instead of a comma here, to have this instead. We'll have the list and then term. So the list becomes the head, and then the term becomes, I don't know if this will work though. Let me give this a shot and see what actually happens here. Okay, so we wrote that, and we're gonna do, just gonna recompile this. Okay, everything is cool. Alright, cool. It's still yeah, no, I didn't really go as I anticipated there. Yeah, now let me not question it for the time being, because I think that's the way it's probably supposed to be for the present moment. But I think that can be done better, because I don't understand why it has to be nested to that. Maybe that's the purpose of the tail recursion. But again, let's see if there might be a function we might be able to use here called list, and then flatten. So we could actually have this return this, and then what we do, yeah. Let's see if we can compile that again, and then because that's actually iffy. And I need to save this. So if we have this, return this, and then we save that into a new list. After recompiling, and basically this will fail because it's not going to match the other side. Can you? I think we might be able to just flash that. Okay. Cool. So now if we do this, right? So now we've got this, and then we can use list, flatten, new list. There we go, and then now that sort of clears that up. So where would we put that flatten if we wanted to? We could maybe put it in here. We could possibly put it in this section here, or even just on this section here. So I think, but yeah, that's pointless at this point in time. But yeah, you can use the flatten command to basically make that function as you'd expect, as opposed to getting these deeply nested lists here. And yeah, and that's pretty much that. The next function is the reverse function. So this basically reverses whatever is in the current list. By taking the head, so basically it does it backwards. It takes the head and basically appends it to the list until, let's see, do we still have list? Oh damn, man. List 1, is it? Okay, cool. Still have list 1, so we can say recursive list function called, sorry, reverse. So we pass in list 1. There you go. So it basically reverses it for us, and basically what it does is it just cycles around it. So basically it takes the 1 and adds it to the 8 there. It takes it to add it to the where it will be 8 1 2 now, and then so on and so on and so on until it produces a new list. As you can see here, and as you can imagine, it just calls the function again and again and again and again, which is pretty interesting. I think it's pretty cool though when you think about it, because it tells, like, it basically creates a new list, and the tail is basically what's left over from after the head has been utilized, which is pretty decent. Okay, cool. So tail reverse, it's pretty much the same thing. The accumulate is basically the final outcome, I imagine. Let's try that. Let's see if we get the same result from that. Yeah, pretty much same result, you know. It does the same thing, but instead of using it basically separates the tail from the pre-existing tail does that. You can see it here. You can see it actually happening here. Takes the list, has an empty list, has the list here, and then the list, this function executes where it takes the head and the tail and the accumulator, which is an empty list, and it has the head with the accumulator has the head with the accumulator and the tail there, which then is the remaining list, because the head would be pretty much here. So it's pretty bizarre the way it works until there's an empty, until the tail is pretty much empty, which is pretty interesting. So it works differently. Let's see what this sublist does. So what's n here? Let's see what the sublist does on that here. Sublist takes list and the number, and the number has to be greater than 0, and basically what it will do is it will take the tail and minus 1 from that number on each recursion. So I'm not understanding exactly what it's doing, so let's see what happens. So if I put the number 3, okay, so basically it takes the list and slices it. Okay, that makes sense. So it'll basically take away this number, and then when this number reaches 0, then pretty much it pretty much stops, returns an empty. Yeah, so which is pretty cool. So so if you put there 5, and here I think it can be any, it doesn't really matter what type you put in. Neither does it on these other ones as well, but yeah. So that's that for sublist. Tail sublist does the same thing, but it does it in a more long-winded way by using the tail. Towards parse the empty list. So basically, I think the tail functions tend to have the sublist. They tend to start with an empty list. They have to be submitted this empty list, which is not really a necessity in my opinion. And the way that the function actually works is a little bit different. As compared to all the sort of the other ones there, the order of parameters are switched a little bit differently there. So the zip function is one that's pretty cool. It zips a list into tuples. We're actually using the zip function as well, which is actually it's alright, I suppose. Actually no, wait, the zip is the okay, cool, yeah, no. So that's pretty cool. It takes two lists and then basically zips them together into tuples. As you can see, it's pretty obvious here. If you understand how this tail head thing works, like just calling the list over and over again, it sort of makes some bizarre level of sense. So if I do the zip, and some of these functions are available in Erlang, by the way, as native functions. So there you go. Pretty much it zips, creates a list of tuples, and you can do that with the varying type of data structures, which makes it really powerful in my opinion. It's actually pretty cool when you think that, when you understand that you can do that. Now the Latium zip, pretty much it does the same thing, but it seems a bit okay. Just because I can avoid the error there. Because for example, let's say if I pass an empty list here, what happens? Okay, we get an error because obviously it needs a thing. But I wonder if I do that to the latent zip, what actually happens here? Okay, yeah. So I just get like an empty list back, right? Rather than the no close exception there. Be cool. That's a latent zip, and the tail zip does the same thing as the zip, but you know, you pass it in list, whereas the empty there'll be an empty list here somewhere. Okay, here you go. Pass an empty list there as the accumulator, and basically when you run this function here, it basically adds this into that particular list. Or at least it's the accumulator. And yeah, that's pretty much that really. You can see how it works. It's weird, but it works, which is the effed up thing. You know, it's the tail functions are weird. I'm not really sure as to in what scenarios they will be useful, but I'm sure there's probably some type of working with particular data types or something that will become useful. And the tail latent function does the same thing, but has a bit more of a sort of error handling mechanism in that you get an empty list if you pass an empty list where you need to pass two lists. So here you have the x's and the y's, which we take the beginning, the head, and then we basically return we put those in the tuple there. As we call the function, we put those in a tuple and call the function again, but with the rest of the x's and the y's, right? If that makes sense, within a particular list. Pretty cool. And the tail latent one just pretty much does the same thing, but it's able to return an empty list when one passes either one of these, which is pretty cool. So this is pattern matching at its best, and well, not at its best, but that's how pattern matching works, especially on functions, which is pretty cool in my opinion. Alright, cool. So I've been at this for a while. The partition looks interesting because it has an if statement which basically defines a pivot. And the LC quicksort as well. See if we can. What's the pivot here? Alright, cool. So I think it's list all equals going for a while here, so let's see if we just okay, right, and then what we want to do here, we're just going to try the partition function, but I'm not sure if I'm going to get this right as it. list alt. So I'm going to say our pivot number is going to be 30. Smaller, larger. I'm not sure if I need to supply that. Let's see if I. Yeah, no. It's gonna need that. So let's see. 5 and 20. Well, it definitely done what it needed to do. Okay, cool. Yeah, that kind of makes sense. So it split the list in relation to which function is like, for example, it basically split it with anything less than 30 to the left and anything greater than 30 to the right. But what did the smaller larger actually do in this instance? Okay, I think smaller larger is just like a label. So what you can actually end up doing, you can actually pass in an atom there. So an atom is like a static value. So for example, if we say why do I even need to define this? I think this would be better off just left there as a and then you can actually then access that tuple. So you can even do things like I think this should work from A and B, and then if you do A, you get smaller, and if you get B, you get larger there. Okay, cool, which is pretty interesting. So that's a pretty interesting function in itself, I think, in general. Now this quick sort here is pretty interesting as well. What's happening here is actually pretty cool. So let's see, let's use the quick sort. And the quick sort, the good thing about it is it just takes the list. That's a long time, man. Almost 30 minutes. LC quick sort. And we're gonna pass it list alt. It was created before. Damn. See, as it just sorts it out in order as you pretty much expect. And the way that works is pretty bizarre, because what's actually happening is this function here actually does it. It actually does a pretty interesting thing in terms of the calculation, rather than actually having something else perform that calculation. What this is actually doing is actually doing that. I'm forgetting what it's called, man. It's a type of mathematical formula. Yeah, it's a type of mathematical formula, so it's if it's less than or equal to the pivot number, and the pivot number is always the current it's always the current number. So it's using tail recursion to actually do the function, which is pretty cool. And I don't know if I'm doing it justice here, but pretty much that's what it's doing here, and it's creating a new list with each pivot. And when we get to the end of this, there basically will be no values here, and depending on what it gets from this function, from this formula here, it'll either be to the left or to the right of that pivot number. Now that's actually a pretty interesting algorithm. Like, I'm not a pro developer, so I can't tell you about what algorithms or how the algorithms actually function themselves. But this is pretty much how that's configured. In my own humble opinion. So if I look at the damn man, I've overshot time a bit, but hopefully it should be alright in terms of video wise. But hopefully you enjoyed, like, sort of seeing all the functions that work there and how they work and how they pretty much function. And managed to get some runtime capabilities there, but hopefully there's a later time I can actually define and actually show this in more depth. Yeah, I think this is a pretty quick sort algorithm. That's it. Yeah, no, it's called a quick sort algorithm. So basically it decides where the number goes based on that, and it's a bit weird to actually understand, because how do you know from which side how do you know from which side the actual number is going to go? But I think it's okay, because what's actually happening is doing this from the head there, but then it's like there's two of them, so it gets a bit iffy, but shouldn't be nothing too much to be concerned about. Because it's doing it recursively. As well. It looks really fucked up, but it sort of it works, and it sort of makes sense to a degree. And I'm not just doing it justice in my explanation here. Because here it does the condition. Based on the current pivot, which would be the current head there, and then that gets appended to here by being returned from that particular function. So it's pretty interesting to say the least. So everything is dependent on these checks here. It's pretty cool. But yeah, hopefully I can cover that at another time if I ever actually go into algorithms with Erlang, but I'm probably not gonna delve too deep into that. But at the moment, just understand that it checks those two functions. It checks that against the it checks the value and adds it to the pivot number here, which we then end up with a new list from my perceptual understanding of things, which is pretty cool, but somewhat complex to a specific degree, or at least it's an algorithm that's simplified drastically, which is pretty cool. So that's that. Did you get the opportunity to go over some of this other stuff here? It would have been good to see like some of these other things working. So here, as you can see, the recursive function and pass to a beam file when you compile it, and then the beam file is then loaded at runtime. So it would be good to go over some of the exceptions just to see those working there, and the records would be interesting to go over, and the guards also would have been good, but obviously I spent quite a lot speaking there. The tree one is intriguing as well. It's basically some recursion coupled with some guard clause there, which is pretty interesting. And the vote is basically the shortest path first algorithm. It uses a bunch of different things to define, but it goes into opening files and things of that nature, or at least reading from files, which is good. So we'll check that there's some bad news there. Yeah, and that's pretty much that for now, but we'll see if we can cover anything else an alternate time there. But that was pretty much that for the recursive functions. I hope it was interesting and sort of made some sense to one degree or another. So I hope you enjoyed that, and thank you for listening to those who did.